Hi. Hello, everyone. Welcome to another Rolled Alloys webinar. My name is Garrett Gildenzoff, and I will be doing a little bit of the introduction and overview of what's going on today. Today's topic, we will be talking on material selection for saltwater reverse osmosis feed lines, as well as brine reject lines. Today's agenda, we will talk about rolled alloys as a whole and what we do here, some of our alloys of interest for this application, some corrosion-resistant alloys and how they respond in this environment, some history on saltwater reverse osmosis materials, a range of those applications, and some customer accreditations. Here at Rolled Alloys, we are a global supplier of materials and alloys, specialty alloys. We offer state-of-the-art material processing, and best-in-class e-commerce site, and a metallurgical expertise team who is speaking with you today. We offer nickel alloys, stainless steels, titanium, and cobalt alloys, and a variety of forms ranging from plate, sheet, bar, pipe and fillings, and other welding consumables. Those state-of-the-art processing capabilities include laser cutting, plasma cutting, water jet, shear, bar saw, and a couple other processes depending on location. And we also offer our metallurgical services. This is our team that is dedicated to being there for our customers with our knowledge in our laboratory. We offer technical assistance. We offer laboratory services. We have a free sample inventory program and also offer lunch and learns. Today's speaker is Dr. Glenn Byrne. Dr. Byrne has obtained a PhD as well as his bachelor's at the University of Sheffield in metallurgy. He is a fellow of the Institute of Minerals and Mining. He's also qualified as a member of the Welding Institute and as a chartered engineer. After finishing his degree, he also joined the Corrosion and Protection Center for Industrial Services at UMIST in '84. He also joined Veer Materials and Foundries in '89 to contribute to the global market on the industries and applications and sales of duplex and super duplex stainless steels. In 2008, in 2008, Rolled Alloys acquired Veer Materials and Foundries, where Dr. Byrne worked, and he also continued to work on his development in the sales and market of duplex stainless steels. And Dr. Byrne also is very passionate on understanding the mechanisms of steel behavior and the reasons behind those failures, and then also exploring ways to improve on them. I will now pass you off on to Dr. Byrne, who will be taking it the rest of the way.
Thank you. So I'd like to talk now a little bit about the alloys of interest. This is a listing of the compositions of austenitic and duplex grades of steel that are commonly used in seawater reverse osmosis applications. The pitting resistance equivalent number of each of these grades is shown in the column at the end of the table. And this is the result of the calculation detailed in this equation below. The PREN is essentially an empirical relationship that's derived from the regression analysis of the composition of stainless steels and the results of their performance in corrosion tests in chloride environments. It's useful characterization of pitting and crevice corrosion resistance of different grades of steel. The alloys highlighted in yellow are the most seawater resistant corrosion resistant in the group, and they all have high PREN numbers that consist of a couple of super austenitic stainless steels and a couple of super duplex stainless steels. Okay, let's talk about corrosion resistance a little. When we plot the pitting resistance equivalent number versus the critical pitting temperature, we find that as the PREN increases, the critical pitting temperature increases too. This is in a linear fashion, you see in this graph. This is also true if we measured the critical crevice temperature. This trend holds for most oxidizing chloride solutions. Initially, the PREN equation was percent chrome plus 3.3% moly, when new nitrogen-bearing alloys were developed with improved corrosion resistance, a term for nitrogen was added to the equation, and similarly when tungsten-bearing alloys became available. For example, Xeron 100, which contains between 0.5% and 1% of tungsten, moves to a better fit position against the regression equation when tungsten is utilized in the regression analysis and the PRN equation. But just to set the scene, I was born in 1957, but it wasn't until the late 1960s that AOD steelmaking, that's argon oxygen decarburization steelmaking, allowed us to make good stainless steel economically. So good stainless steel steelmaking practice began when I was about 10 years old. Similarly, the first RO membranes were developed in California in 1959. The development and understanding of both stainless steels and membrane technology occurred more or less in parallel, and both technologies are about as old as me. Activity in measuring the corrosion resistance of stainless steels, occurred more or less in parallel. Activity in measuring the corrosion resistance of stainless steels and its correlation with composition was high in the 20 years from the late 1960s through to the late 1980s. It was in the late 1980s when the commonly accepted PRN equation was first published widely. Over this period, manufacturers claimed that most stainless steel grades from 316 upwards were suitable for marine applications, and this led to some problems and frustration for many industries. This claim was based on testing in environments other than natural seawater, for example, artificial seawater, various sodium chloride solutions, ferric chloride solutions, and other acidic chloride solutions. These tests provided a ranking of alloys, but there was no reliable correlation between these tests and real seawater service performance. In the early 1980s, companies like Shell were looking to replace copper alloys with stainless steels in seawater cooling and fire protection systems on offshore platforms. Their approach was to initiate a 4-year-long research program of testing of stainless steels and nickel alloys in the North Sea. They based their material selection strategy for future projects on the results of this work. In this next slide, I show the generally accepted safe use limits of chloride for these alloys of interest. These are considered to be a good rule of thumb figures. 304L, for example, the red line, is good up to about 200 ppm chloride, but for performance between 200 ppm chloride and 1000 ppm chloride is limited. 316 is good up to 200 ppm to 1000 ppm chloride, as you see here. And 2205 and 904L is good from 1000 ppm chloride to about 3600 ppm chloride. Above this limit, you rely on 6% molybdenum superaustenitic stainless steels and 25% chrome super duplex stainless steels. But of course, these limits are subject to some provisos that I also refer to in the slide. There's presence of other species in solutions, the severity of crevice, the fabrication practice, and microbiological activity, and limits of chlorination. This is too much to go into for the purpose of this discussion, but the references that I refer you to in this checkout section give you some good background information. For example, the more conservative limits that I show here for 304 and 316 arise when some of the provisos detailed here work against you. The figure on the left shows the potential of stainless steels in seawater, how it varies with water treatment. This is important because the higher the potential, the higher the risk of pitting and crevice corrosion. The figure on the right is a schematic representation of a seawater reverse osmosis plant. For a stainless steel in natural seawater, the potential is about 350 millivolts versus the standard Kalem electrode once the biofilm has formed. If the seawater is disinfected continuously with about half a ppm of residual chlorine to prevent fouling, the potential is typically plus 600 millivolts, as you can see here. And this actually prevails from the seawater intake, because chlorine is usually added through the intake pump, up until we get to this point where the chlorine is neutralized. So this prevails up to this condition is 20,000 ppm at 600 millivolts of potential up to this point in the system. The chlorinated feed then has to be dechlorinated before it reaches the membranes, as the membranes are normally chlorine intolerant and would be oxidized. This gives a high salt passage into the permeate that you don't want. The dechlorination is done by adding chemicals like sodium metabisulfate, and this is an oxygen scavenger by nature, and it pulls the potential down to the range plus 200 to plus 100 millivolts, depending on the dosage. And this is a range where the membranes tend to work at their best. So we have this condition up to the membranes, where after the chlorine neutralizer, we have treated seawater with a chloride content typically of 20,000 ppm at plus 200 to 100 millivolts, going up to into the HP pump and beyond. After RO, we have two lines. We have the permeate water, where typically the chloride content's very low, sort of 250 ppm chloride and less, at a potential of 200 to 100 millivolts. And the brine reject line, which is typically 30 to 40,000 ppm of chlorides, again at 200 to 100 millivolts. So the brine reject pipework and the energy recovery devices see these more severe conditions. So a little about some of the history of seawater reverse osmosis. I'm really looking at plants that were being constructed in the Middle East and elsewhere in the early 1990s in this slide. Grades like 316 were being promoted for seawater service, and there was little or no pilot plant testing of the materials. Industry focus was on membrane performance, energy usage, pre-treatment, etc. There was nothing with respect to materials of construction or pilot plants. You can see from the table that unlike Shell, this industry's alloy selection strategy was to do this by rote, starting with 316L and escalating an alloy content and cost until a satisfactory level of corrosion resistance was realized. And you can see this in the Saudi progression of projects. I've highlighted these in blue. So the early Saudi projects, 316 and 316 here, and then they didn't work out so well because they suffered pitting and crevice corrosion. So they were moved to the next alloy up, 317. That suffered crevice and pitting corrosion, and then they gravitated to 6% molybdenum alloys by around about 1986. So from 81 through to 86, it was trial and error, but the 6MO worked quite well. In some applications, the performance of low-grade stainless steel was quite catastrophic, corroded very quickly. If you look at these three projects in Malta, 316 was installed in 1986, and by 1989, it had to be replaced with 6% molybdenum alloys. Again, in 1987, this particular project built in 316, and by 1990, it's had to be replaced with 6% molybdenum alloy. And similarly, for this job, in 1988, it was built in 316, and by 1991, it was replaced. Once it was replaced with 6MO, the performance was very good. In other projects, it took time before corrosion became a problem. 316 and 2205 and 904 alloys performance was mixed in the short term, but generally within 5 years it had widespread corrosion. There was still claim and counterclaim as to the usefulness of low-grade stainless steels, but with time their limitation became apparent, even in the cold seawater of the North Sea. By the 1990s, trial and error had largely established that 6% molybdenum superaustenitic stainless steels were the best solution for warm seawater service. But it wasn't until 1993 that the science caught up, and we had a simple lab test that correlated with corrosion resistance in seawater and focused our attention on the starting point for what we needed from a stainless steel for good seawater service. And that's a minimum PREM level. The graph on the right shows, at the top right, shows the results of crevice corrosion tests in both real seawater and in ferric chloride solution. The range of stainless steels of duplex, austenite, and ferritic metallurgy were sampled and exposed to natural seawater, mostly in the east coast of the United States, for a period up to 2 years. Then it was removed from the seawater, and the number of sites of corrosion attack underneath the crevice washers was measured, and that was compared against the critical crevice temperature measured in the laboratory in ferric chloride solution. And what was found was that the number of sites of crevice corrosion in seawater diminished as the CCT in ferric chloride solution of the alloys increased. And for alloys with CCT in ferric chloride solution greater than 35 degrees centigrade gave very good performance in seawater. So then you can replot this, and you can plot the CCT in ferric chloride against the pitting resistance equivalent number of the ferritic, austenitic, and duplex grades. And the metallurgies of these alloys then begin to differentiate. So you can see, if you draw a line at 35 degrees C in ferric chloride, the implication of that is that you need a PREN of 35 degrees C in order to give good crevice corrosion resistance in seawater. Similar for duplex stainless steels, you need a minimum PREN of 40 to get good crevice corrosion resistance in seawater. And for the austenitic grades, you need a PREN of 45, again, to get good crevice corrosion in seawater. So the use of 6% molybdenum alloys for high pressure seawater feed and brine reject pipework grew from 1986 onward as awareness of its good performance spread. Here I'm plotting the installed capacity of these grades of steel against a timeline. The newly developed super duplex grade 0100 entered the market in 1992, with 2507 following in the early 2000s. Better technical understanding of what was required of stainless steels for seawater service, the super duplex stainless steel service history of pipes in oil and gas in seawater cooling and fire protection systems, and as castings in seawater pumping applications, as well as its highest design strength and its significantly lower cost than 6% molybdenum alloys, contributed to its acceptance for seawater reverse osmosis applications. This realization also coincided with a technology transition in the industry and a move from MSF and MED to seawater reverse osmosis technology. Seawater reverse osmosis was increasingly more energy efficient, cost effective, and scalable. The new plants were generally bigger than before, 100,000 to 300,000 cubic meters a day, and there were more of them. So the installed RO capacity of both 0100 and 2507 soared over this time period, while the utilization of 6MO tended to lag. And this is primarily because of its lower cost. The super duplex alloys tend to be about 30% lower in cost than the super austenitic stainless steels. Our installed capacity for 0100 and 2507 as rolled alloys now exceeds 2.7 million cubic meters a day, and you can see the timeline for this installed capacity incrementally growing over the years. We have installations around the world, and indeed we have something like almost 1 million cubic meters a day, or 902,000 cubic meters a day, installed in the Middle East, which is a very arduous application. We've supplied, in fact, 10 projects in the UAE since 1999 through to 2022, as shown in this picture here, with a total capacity of 413,000 cubic meters a day. So this side here is the Persian Gulf. This side here is on the Gulf of Oman in the UAE. Now, typical Persian Gulf seawater temperatures are in the range 20 to 35 degrees C, and salinity is about 4.5%. This compares with Monterey Bay in California, where the seawater conditions range from 10 degrees C to 19 degrees C, with a salinity of 3.3%. But seawater intake temperatures are not always at ambient. Around 2002, we had the Tampa Bay Water Project, and this plant was co-located with the Big Bend Power Station at Apollo Beach in Florida. It used the output of the power station's cooling water as the seawater feed, and this had a design temperature of 43 degrees C. This avoided the need for a new seawater intake system to be built, so there was no pilot test plant of materials of construction. The capacity of this job was 25 million gallons a day, or about 106,000 cubic meters. So trial and error in material selection wasn't an option. We had to technically justify the application of super duplex stainless steels and superaustenitic stainless steels for this job. And I'm going to discuss that in more detail in another webinar. So let's talk a little bit about applications. Our applications range from pilot plants like this one that was installed in Long Beach years ago, to small size plants for hotels and golf courses, holiday island resorts like this one in Adeke in the Canary Islands, and other sort of coastal towns. We also supplied medium-sized plants for power stations in the Philippines and industrial independent water suppliers in the Kingdom of Saudi Arabia and the United Arab Emirates. We've also been involved in a number of rather significantly larger plants between 100,000 and 300,000 cubic meters a day for municipal jobs in the USA, mainland Spain, Algeria, India, Morocco, Kingdom of Saudi Arabia, UAE, and Australia. We also supply plates for cartridge filter vessels and filter baskets, and pipes to energy recovery equipment manufacturers and pressure vessel manufacturers to make these side ports that are set into the vessels, and these are deployed on many projects around the world. This is some information on what we found to be a challenging project that we completed in 2019, and from a logistics point of view, it was very challenging. It consisted of 1,200 fabricated super duplex stainless steel spools with a capacity of 237,000 cubic meters a day. Sets of pipe spools were distributed across eight job sites down the west coast of Saudi Arabia, on the Red Sea coast, and specific numbers of spools were supplied in a phased delivery schedule to each of these job sites to meet a strict fabrication schedule. So 6% molybdenum alloys and super duplex stainless steels have performed well in our applications around the world, but they're not immune to corrosion in seawater. Crevice corrosion at couplings and at threaded connections and at flange faces, and pitting corrosion of welds can be an issue. It can be relatively trivial, but it can be more serious. The relative cost of super duplex stainless steel is about twice that of 316L. 6% moly alloys, the price is about 2.8 times 316L. The next generation of high alloy stainless steels and nickel alloys are 5 to 8.5 times the cost of 316L. And this precludes their use in place of the more affordable duplex and super duplex stainless steels. Now, seawater corrosion testing shows significant scattering results caused because there are numerous contributing factors controlling the initiation and propagation of pitting and crevice corrosion. Probabilistic algorithms have been developed to try to model this behavior, but this is for the academics. The stochastic nature of the problem means that adherence to best practice in manufacture, heat treatment, acid pickling, and fabrication of these pipe spools can be very cost effective in minimizing the risk of corrosion. And I want to discuss this in more detail in the next webinar early in the new year. And I want to share what we've learned about simple methods to improve corrosion resistance and reduce the risk of leaks in this webinar. So here we see some customers we've supplied to around the world. We've had repeat business from many of these customers over the years, and they've increased the capacity of existing plants or built new ones. So I hope that I've demonstrated that rolled alloys have a specific expertise and highly experienced supply chain capability for seawater reverse osmosis projects. We can deliver quality materials of construction and technically support the scope of supply, and we'd welcome the opportunity to work for you in this market. That's where I'd like to end the presentation and be happy to take any questions.